All right, everybody, I think we're ready to get started. How is everyone tonight? Good, good. Thank you all for being here for our August Meet the Astronomer. We were really hoping we'd be able to be outside, but I think we would literally burst into flames. So we moved it in here. I don't hear any complaints about us being in here under this AC. So hopefully in September, though, when we do our next Meet the Astronomer, we will be out on the back patio under pleasant weather, listening to the crickets as we're listening to a wonderful talk. So thank you all for being here. We are also we're also streaming this via YouTube to some folks that are watching from afar. So tonight, the program will be, we'll have roughly an hour for the lecture, maybe a little bit less than that. I will try not to go over that hour because there's so much good stuff to talk about. Then we'll do a Q&A, and folks that are watching on YouTube, if you have questions, just go ahead and pop those questions in the chat, and we'll get to them when we do the Q&A. And then we're hopeful that it's going to be clear afterwards. It looks like it's heading that way, so we'll have the main telescope open to hopefully do a little bit of viewing. And if you've never been here before and it's too cloudy to view, make sure you go up there and check it out. It's pretty impressive. So one other announcement, be sure to follow us on Eventbrite, which is where you purchase the tickets for this program. If you click that blue follow button at the top of the page, it will alert you whenever we have another event listed on here. So we hope to see every one of you up here many more times. But let's go ahead and get started. So tonight, we're going to be talking about one of the things that I like talking about the most, and that is light, and how the universe has been very kind to us and has given us a way to study it when we can barely get out into our solar system. So there have been a tremendous number of people over the centuries that have figured out how to decode this information and teach us about the universe. So tonight I'd like to touch on a few of those. And like I say, there's so many more things to talk about, we're just not going to have time for them tonight. But we'll start with a very brief refresher, make sure everybody's on the same page in terms of terminology and some other little facts about light. And then there are three main things that we'll be talking about in terms of the science, and that's figuring out compositions, velocities of objects, and how we know temperatures of things such as stars. And if time permits, we will also take a little bit of a peek as to what some of these beautiful images from the Hubble Space Telescope, the Webb Telescope, and even amateur telescopes are giving us. Okay. Give me 1 second. I think I'm getting a little reverb there. Can everybody still hear me all right? Okay, cool. All right, so just a bit of a background here. Light in general can be thought of as an electromagnetic wave, or in other words, the electric and the magnetic fields permeating our universe are oscillating, and that creates a wave of energy. But we can also regard light as a photon, which is a discrete packet of energy, and we thank Einstein for that theory. But light travels at the speed of light for that medium. So when I say, is it possible to travel faster than the speed of light, the correct answer is? Anybody?
No.
It depends. It depends is always a good answer, right? So it does depend. If we are talking about light traveling through this room, it is indeed possible to travel faster than the speed of light as it goes through this room because the air is slowing it down just a bit, only by about 1%. But nevertheless, things like particle colliders are able to accelerate protons and neutrons and electrons up to speeds that are faster than the speed of light in this room. However, if we're talking about light as it is traveling through empty space, that is the universal speed limit that so far, as we can tell, we cannot break that or even meet it with anything that has mass. It would literally take an infinite amount of mass or infinite amount of energy to get a little bit of mass up to that speed, okay? So this C is our universal speed limit, all righty? Now, when we talk about the light, we can describe it in terms of things like wavelength. So if we picture it as a wave, which is the way we're going to be talking about it most of this evening, you can describe those, or the lengths of those waves, not the height, but the lengths. And I've got two examples here of a long wavelength photon on the left and a short wavelength photon on the right. And you may have also heard of frequency. That's just the number of waves that pass a given point each second. And so those two values are inversely proportional. If one goes up, the other goes down, but they are related. How does wavelength relate to energy and to color? Well, if you have a shorter wavelength photon, then you have more energy packed into that, and you have light that is bluer. And conversely, longer waves are redder, and they have less energy. Now, that doesn't just mean we're talking about the rainbow. We can be talking about light that has very low energy, like radio waves, or light that's very high energy, like X-rays or gamma rays. So when we say light is bluer or redder, we're not necessarily talking about blue or red. We're talking more about, is it moving towards the high energy end or the low energy end, okay? And then finally, we've got a little bit to discuss about the atom. So thankfully, the atom is set up like this so that we are able to learn about our cosmos because of the way these atoms behave with light. So just as a refresher, we've got our nucleus at the center that has protons and neutrons, and then around that we have these electrons. And even though this is no longer the correct model of the atom, for our purposes of discussion, it's a great analogy to talk about how electrons absorb light and emit light, okay? We good back there, Tommy? Okay. So these electrons, we can view them as having little orbits like a planet going around a star, but in reality that's not quite the case. But just kind of picture this model when we're talking about the electrons in their atoms, okay? One little caveat here I always like to mention. So in this depiction we have a carbon atom which has 6 protons and in this case 6 neutrons in its nucleus. If I had an atom that had 7 protons in its nucleus, would it still be a carbon? It would not. It would actually be a nitrogen. But what if I had 6 protons and 7 neutrons? Would it still be a carbon atom? It actually would. So the type of element, whether it's carbon, oxygen, uranium, whatever, that is determined by the number of protons. The number of neutrons determines what isotope we have. So if you've ever heard of isotope and you're not familiar, that's what it is. It's basically a different flavor of this atom. So let's talk a little bit about spectrum. We've all seen spectra in many shapes and forms over the years, and so when we see a rainbow, we are seeing the spectrum of the sun. And when we say spectrum, all we mean is that we're taking the light from an object and we're breaking it up into all of its component colors. So with white light, like from the sun, we have all of the different colors of the rainbow. If you have a laser, for example, you try to break its light up, it doesn't actually break up because by definition, lasers put out one specific color of light, okay, one wavelength of light. But when we look at this, we think, okay, we're seeing every color of the rainbow, and we've all seen this many times, but if we carefully look at the sun spectrum, it's not all quite what it seems. So this is a close-up of the solar spectrum, and you can see that there are these faint dark bands running through that spectrum. It's not an artifact of the photograph or just a bad photograph somebody took. These are actually real lines, okay? And so these real lines were first discovered a little over 200 years ago by William Hyde Wollaston. He was the first one to really report the existence of these lines in the solar spectrum. And when you go out and look at a rainbow, you're not going to pick those out by eye. You have to have a really good stretched out rainbow to be able to start picking these out. A little over a decade later, Joseph von Fraunhofer also independently discovered these lines, but he spent a lot of time studying the structure of these lines, and he really mapped them out in the solar spectrum and ended up with about 500 lines in the entire solar spectrum. So none of these guys really knew what was going on, but they knew that these lines were definitely present in the solar spectrum. And it would be about another 60 years or so before we'd start figuring out what the deal was with these. Actually, a little bit longer than that. But now let's take the solar spectrum and stretch it out even more. So this is a spectrum of the sun from a telescope at Kitt Peak Observatory in Arizona called the McMath Pierce Solar Observatory. And what they've done here, they've created something called an échelle spectrum, which échelle is a French term for ladder, because basically this spectrum has been spread out and it's been cut up and stacked like rungs of a ladder there. And so you can definitely see now that those lines are present, and you can also start to see details in those lines. For example, there are lots of deep dark lines. There's some really faint ones in there. There's some that are pretty broad. There's some that are very narrow. There's a lot going on in here, okay? So folks were really trying to figure out what the deal was with these lines, and also beginning to wonder if other stars would have these lines as well. And spoiler alert, they do. But then we go forward a little bit more, about another 40 years or so. Gustav Kirchhoff and then Robert Bunsen, the namesake of the famous Bunsen burner, were studying the solar spectrum. And Bunsen took this burner, and the deal with the Bunsen burner is that it is a very, very efficient burner. So if you look at the flame of a Bunsen burner, it's almost colorless because the combustion is so complete, which means that if you put a sample in that flame and it starts to combust, whatever light is coming out of that is from that sample. So they began experimenting with placing different samples in the flame to see what kind of spectra they got, and they noticed that those spectra were very different depending on what you put into combust. But what was more interesting was that they started to notice a correlation between the individual colors given off by a sample of material. Let's say it was carbon or aluminum. It was very it correlated very well with what they were seeing in the solar spectrum. In fact, they would see a pattern of lines, and they'd start to be able to see that same pattern missing in the sun's spectrum. And so that couldn't have been coincidence. They thought, something's got to be going on here. These are two related phenomena. And they were correct, but it would take a little while before we finally figured out what it was. So I'm going to give you a fun little demonstration with some spectra. We're going to, instead of burning some things, which I know is lots of fun, but we're going to do it a little bit more safely. We've got up at the front here some different light sources. And some of our volunteers in the back are going to be passing out some special glasses, and you all get to keep these. These glasses are known as diffraction grating glasses, and you may have seen these before or used them at like a fireworks show or on the holidays, but you look through them and you see a rainbow around everything that has a light source. But we're not going to use these just for fun tonight. We're going to use them for science, okay? So we're going to continue passing these out, and while they're doing that, I am going to mute our screen because we're going to want it rather dark in here. Since I remember how to do that, okay? And then once they're passed out, we'll turn off some more of the lights. And then we've got some light sources up here. Okay. And if you don't get a pair, please raise your hand, let us know. We've got plenty for everybody. So yeah, they've got little creases. You can fold those on the creases, pop them on. If you've got glasses on, you can just put them over your glasses. You don't have to put them under. But one thing I do want to point out, and this is extremely important, do not try to observe the sun spectrum by looking at the sun with these. It would be basically no different than you just staring straight at the sun. These are not solar glasses. Do not try to observe that solar spectrum. You can try it, but you're not going to see it anyway, and then you have eye damage. So please don't do that, okay? All righty. All right, everybody's got a pair now? All right, we're going to start out with, I've got one of the classic light bulbs over here. It is an incandescent bulb. I'm going to set it up to where you can see it a little bit easier. I turn that on. I know, you see, this is why I like doing this talk. That moment when you first turn on that very first slide, yeah, it's nothing like it, right? All right. So these glasses, the plastic in that actually has rulings or little grooves. There's about 13,500 per inch. So they're so small you can't see them, but when light passes through these grooves, through processes of diffraction and interference, something you all can look up when you go home, the light spreads out into a spectrum. And it actually works much better than a prism. Okay? They are groovy glasses, right? I mean, we could just stop the talk right now and just stare at the light and it'd be fun, right? All right. But what you're seeing, so this is an incandescent light bulb. It's got the metal filament in there, and you are seeing a complete rainbow. Unlike the sun, which had those dark bands in it, this spectrum you're going to see does not have dark bands in it. It is a true complete rainbow. It is technically known as a continuous spectrum for obvious reasons. There are no gaps, okay? So this is going to be one type of spectrum that we're going to be looking at, and there's 3 total, okay? Now, I'm going to turn this light off, and we have a different light over on the other side. Actually, before I do that, you can see it. This is a little compact fluorescent light bulb, one of the kind of corkscrew type bulbs that we're still kind of using, but they're kind of going out of fashion as well. Put that down. This one's not as bright, but it's fun. Okay. So one thing you're going to notice is that this one, you can see the actual shape of the bulb as well. And we haven't forgotten our folks at home that are watching from afar. We've got one of these pairs of glasses over the camera so they can get kind of an idea of what we're seeing. But one thing that you will notice, well, first of all, I forgot to mention, you're going to see multiple spectra. They're all the same, but they spread out more the farther they are from the bulb, okay? But now, for example, I can see about 1, 2, 3, 4. I can see about 6 different images of the bulb in different colors. Okay, I don't see every color of red or every color of yellow or green or blue. I'm seeing certain colors coming from that bulb. But when we add all those different colors, we basically have one from the blue region, one from the green, one from the red, one from the yellow. You add them all together, and you get a nice white light. Okay, so but you aren't seeing a continuous rainbow of color. You are seeing individual bands of color. And in fact, if I even kind of shade it just a little bit there, or if I kind of make a little mask, it makes it easier to see those colors. Okay? So we're seeing a different type of spectrum. This is called an emission spectrum. Light is obviously being emitted, but the reason this is called emission is because we also have a third type we'll see in a moment called an absorption spectrum. In fact, you saw the absorption spectrum. That's what the sun's spectrum is, okay? Certain colors of light were absorbed out, all right? Now, I'm going to turn this one off. Well, actually, before I do, I'm going to give you an idea of what we've got here. So the other 4 light sources we have are in these very narrow bulbs. These are transformers, so when I turn these on, we'll run about 10,000 volts through the bulb. But in each of these bulbs, here's an example of one, in each of these bulbs is a particular element. Okay, the bulb has been evacuated of air, and then a specific gaseous element has been pumped into this. Okay, these won't be as bright. Turn this off. All right, I think you'll be able to see it despite those lights back there. I'm going to kind of scoot back to where I can see what you all are seeing. Yeah, you can kind of see it. This one is not the best example, but what you should definitely see is there is a bright red line. Can everybody see that? Yeah. Okay. All right, so within this bulb is a specific element. Let's compare it to this one over here, which has a different element. This one, you can see it a little bit better. Let me raise it up for you a bit. Everybody see that back there? Okay. Set it back down. It's kind of humming on me there. So what we have in each of these bulbs, like I mentioned, is an element. This one to my right, or to your left, is hydrogen gas. This is helium. Okay. Let me turn these off. I've got 2 more I want to show you. This one everybody should be able to see pretty well. This is another element from the periodic table. I'll give you a hint. Both of these last 2 are on the very right side of the periodic table. Anybody want to guess what this one is? Starts with an N. Neon, very good. All right, so neon signs are neon signs because they actually do have neon in them. The red signs you can go up and see, and you can see that when they're off, the tube is actually clear. Whereas other colored signs, they have different powder coatings on the inside to help produce different colors. And then this is our fourth one and our final one. It's not quite as bright. Anybody want to guess? Starts with a K. Krypton, very good. Not kryptonite. Everybody says kryptonite. That's not real. Krypton is real, okay? But one thing that I hope that you noticed was that each of these produces a unique pattern of colors, okay? This pattern of colors is pretty much like a fingerprint for these particular elements. In the display back there against the wall, there are some more of these bulbs in there. So after the talk, if you want to get one of our volunteers or staff, we can show you those. But every one of these elements, every molecule will put out its own unique set of colors. And even though like hydrogen and helium both had red, and this one definitely has reds, those reds are actually different energies. So not even a single line is shared among the elements. So if you identify a line or a color present in the spectrum of an object, and you can match that up to an element here on the Earth, you know what that object has in it, okay? And we'll talk some more about this just to kind of bring it full circle here in just a moment. All right, you can keep your glasses on if you really enjoy them, but we're going to be going back to the screen here, but some people like to keep them on and continue to talk. So here's what the first bulb, that first vertical bulb that had the hydrogen in it, this is what you would have seen if we'd had a really good quality bulb. Unfortunately, I didn't get the right one out. But you saw the bright red line. There was actually a teal and two violet lines. There was a bit of a rainbow, because again, this wasn't our best quality bulb, but you didn't really see that rainbow in the other lights. So like the second light that we saw, you saw this spectrum, and that was our helium bulb. I've got three more up here that we didn't see, but you can see they start getting pretty complex. This is oxygen. Anybody want to guess? You have it in your blood? Iron. This is iron. Getting pretty complex. And then finally, this one is almost a complete spectrum. This is thorium, okay? So again, you know, even though it looks like, especially with iron and thorium, it's like, okay, you got to have some colors overlapping. They got to be sharing some colors. But you got to keep in mind that if we stretch this spectrum way out, each of those lines would be super thin. So on the screen, they look very wide, but they're all different colors. So iron doesn't share any colors with thorium, which is hard to believe, but it's true, okay? All right, so what is the setup for something like this? Let me move this down. So to see these three different types of spectra, we have to have two things. First of all, on the left side of the screen, we have a source of continuous spectrum, and in parentheses it says black body. So in physics, a black body is this theoretical object that is a perfect emitter and absorber of radiation. What we're concerned with is that if it gives off light, it gives off a continuous spectrum, okay? Solid objects tend to do that very, very well, okay? Now, if we just have our glasses on and we're looking at that hot solid object like we were doing with the incandescent light, we see that nice continuous spectrum. But now we need a gas cloud. Let's imagine it's a gas cloud of helium, okay? We pop that up there, and then we position ourselves so that we're looking through that gas cloud to our continuous spectrum, okay? Now what happens is the gas cloud is made out of certain elements. Those elements can absorb and emit certain colors of light. So as all of those different colors are going through that gas cloud from the hot solid object or the black body, certain ones get absorbed. And so when the light that does get to us, we start to see these dark bands because that light's been absorbed by the gas cloud, okay? Now, let's position ourselves, instead of looking through the cloud at the black body, let's just move off to the side so we're just seeing the cloud. Those atoms that absorbed those certain colors, they can't just keep absorbing over time and not emitting something, okay? So these atoms will tend to only hold on to those photons on average for a few millionths to a few billionths of a second, and then they re-emit them, okay? They won't emit them right in the same direction they got them from. They emit them in all directions, okay? So when we look at this cloud, let's say from the bottom of the screen, and we don't see our black body, we can see some of those photons that they absorbed being re-emitted, okay? So that's the scenario for each of these. Now let's talk about why those atoms do that. So atoms have energy levels. Remember we talked about, we showed that diagram where they had the nucleus at the center and we had the little electrons going around. Those are called orbitals. And each orbital, each energy level has a specific energy, and that does not change for an atom. Okay, so according to quantum mechanics, orbits have specific energies, and electrons, they have to be in one of those orbits. They can't be in between. They're basically stuck to those orbits. So they can go up to a higher energy orbit if they absorb the right amount of energy, and then they can also go down energy. They can go down to a different level if they release energy, but they have to absorb and emit certain types of energy, okay? So there are no in-betweens. These values are quantized, hence quantum mechanics. So let's imagine we have a simple atom here. Here's a little electron going around our nucleus. So for hydrogen, well, for any element, the electron wants to be in the ground state. That is the lowest energy state. It is the most stable state. It wants to be in that state. All the atoms, electrons want to be in that state, but we can't cram them all in there, but they want to be, okay? So if we're in the ground state of hydrogen, and as light from our black body is coming through, if a certain color, which equates to 10.2 electron volts of energy, comes through, that little electron can absorb that and jump up to that next level, because that's the energy, the precise energy required to get up to that level. If it was 10.21, it can't do it. There is no in between. It's got to absorb that certain color. Let's say it's in that second level, and then a 1.9 electron volt photon comes through. Guess what? It can absorb that one now and jump up to the third level. And then 0.7 will get it up to that fourth level. All right, so there are different energies it can absorb for its energy levels. Now, it doesn't have to go sequentially like that. It could do, that's off to the side. What that was supposed to show is it going from the number 1 to the number 3 level. And you can see that that's 12.1 electron volts, which that's just 10.2 plus 1.9, okay? Or it could have been at the very ground state and jumped up to that fourth level if it had absorbed 12.8 electron volts, which is a certain color of light. So there are different colors that it can absorb to do these different jumps. And then likewise, when it's in those outer levels, it has to emit those same types of photons in order to get back down, because again, there are no in-betweens, all right? One other thing I didn't mention is ionization. If you noticed, as we were going up in energy level, the energy difference between those levels was getting smaller and smaller and smaller. And you may say, well, wouldn't it eventually go to zero? That would be like going to the infinite level, okay? And for hydrogen, if you start adding up all those different levels, it eventually goes to about 13.6 electron volts. And you say, well, what happens if one of those photons comes through and the electron's in that ground state? Well, if it absorbs it, it gets so much energy, it can completely leave the atom. So the atom is stripped away from the electron is completely stripped from the atom, and it goes careening off somewhere else in the universe. Maybe it encounters another atom, but we say that the atom is ionized now. Okay. So we talked about how in this case here, when the electron is absorbing, it is creating the absorption spectrum, and when it's in a high energy level, like here, and it goes down in energy, it creates an emission spectrum. But how does it create a continuous spectrum? What is that filament in that light bulb made of? I think I heard it back there. It starts with a T. Tungsten. So that is an element. It has electron orbits, and yet we see something like this. So what is the difference here? The difference is that in that bulb we had a solid. So if we have just, and let's say this is iron. If we have our iron atom and it's just out in the universe, it has all of its different electrons and their energy levels. These are the colors that it can emit and absorb. Okay? And when we have a big gas cloud that has lots of these atoms, those atoms are typically so far from one another, they don't feel the electric field of their neighboring atoms. So it's kind of like, they're alone, and they have these nice, pristine energy levels. And for every iron atom, those energy levels are going to be the same. But now let's start cramming them together. Let's start making that gas very dense. What happens? Well, now the electrons start to feel the influence from their neighboring atoms. The electron orbits get distorted. So now the atom on the left, it's got to have a bigger energy level to traverse. So it's going to absorb and emit a higher energy photon, whereas the one on the right, the levels are closer together. So now it's going to absorb and emit a slightly lower energy photon than what it would normally do. You do this with 10 to the 23rd atoms, you're going to get all these possible variations in state. And so what starts to happen as you get this gas denser and denser so that the atoms are starting to feel one another, those nice individual lines start to get smeared out. And eventually when you get a high enough density, they get smeared so much that they blend together. Okay? Sorry, that was way on the bottom there. So if we took the tungsten out of that filament and put it in one of these other bulbs and vaporized it and then turned on the bulb, we would see a nice emission spectrum. Okay. All right. So like we mentioned before, our solar spectrum, this is an absorption spectrum. So what's doing the absorbing? What's doing the emission of that continuous rainbow? Well, the lower layers of the sun, so starting to go down into what's called the convective zone. We don't have to go deep. I mean, just down where the gas is starting to get thick enough where we can't really see past the edge. The gas is dense enough that we're getting a continuous rainbow of light coming out. Okay? That rainbow of light is going out to the atmosphere of the sun. And so that gas is thin enough that it's now able to absorb out its certain colors. So if we took away that atmosphere of the sun, our solar spectrum would be pretty much a continuous spectrum. And speaking of the sun, we actually discovered helium in the sun before we discovered it here on the Earth, thanks to spectroscopy. During a total solar eclipse in 1868, an astronomer by the name of Janssen was observing a spectrum of the sun and noted that there was this yellow line that he couldn't attribute to any other element, and it was found in the spectrum of the sun. So it was suggested by Sir Norman Lockyer that this be named after the sun, because maybe there's an element in the sun that's not here on the Earth. So it was named after Helios, and it's now called helium. But we would later discover it about 30 years later. It's actually mostly found underground. It's a byproduct of elements like uranium and thorium decaying. When they break apart into other elements, they release helium. Okay. There was another element or another mysterious line. This time it was a green one that was discovered in the solar spectrum. We'd already named one element out of the sun, so we couldn't call it helium-2. So they called it coronium for the corona of the sun. But it was later discovered, about half a century later, that this green line was actually due to iron that had already been discovered in the solar corona, or in the sun. But because of the extremely high temperature of the corona, that's about 1 million to 2 million degrees Celsius, some of those atoms, they lose some of their electrons, and that alters their spectrum. Okay. I think one of my favorite discoveries out in space, and sometimes I'll get a question like, what's the point of observing out in space? Why study astronomy? And besides the fact that we are innately curious about everything, we can actually learn a lot about what's going on here on the Earth by studying what's happening in space. And sometimes space will give us a laboratory that we can't replicate on our planet. And that was the case for this element that was going to be called nebulium, after nebula. So it was around the 1850s, 1860s that spectroscopy really started to take off as a science, and it really started to take off in astronomy. Telescopes had been around for a while, and many objects in the sky that were very nebulous, very cloud-like, had been discovered. Some of them had mysterious kind of spiral structures, so they were called spiral nebulae. We now call those galaxies. But then there were other clouds that really didn't necessarily have a certain structure, and they were still called nebulae. When astronomers began observing these spiral nebulae, they saw that it was almost like the spectrum of a star, and that's because these galaxies are made out of billions of stars, and we're seeing the collective spectrum of all those stars. But when they observed objects like this is the Cat's Eye Nebula, they saw that it had an emission spectrum. So they knew this had to be a cloud in space. But one of the bright lines, actually two lines that they discovered, and you would actually see if you looked at this object with a telescope, they were these green lines, and they could not attribute those to any elements. But later on, once quantum mechanics came about, we started learning more about how the electrons can move through energy levels and how long they can stay in those energy levels. And it was found that these green lines were actually just caused by oxygen. And the reason that we couldn't really replicate that on the Earth was that in order to get oxygen to do those two lines, you have to have an incredibly diffuse gas. All right? So this nebula, it looks like there's a bunch of stuff there, which there's about a star's worth, but that's spread out over a few cubic light years. So the densest part of that nebula would still be less dense than the best vacuum that could be created here on Earth in a laboratory. So atoms can behave a little bit differently, and they can go through these other transitions that we can't recreate here on the Earth very well. Okay, so again, that's just one of the ways that the universe has taught us a little bit about how things work. All right, so I think we've covered composition fairly well. I just want to touch on a moment how we can determine things like velocity. So you all have encountered the Doppler effect before. You've all heard, a police car as it's coming towards you, the siren's high-pitched, and the moment it passes you, the pitch goes down. Okay? You can even listen to just a car coming towards you, and the road noise from the tires is higher pitched until it passes you, then it's lower pitched. In the diagrams here, imagine we have a siren. That's the little red thing flashing in the center, and it's sending out sound waves in all directions. The diagram on the left has the siren stationary, so the sound waves are going out uniformly. The right side, we have the siren moving to the right side of the screen. And you can see how, as it's moving to the right, the waves to its right side are compressed due to its motion. Okay, so the waves are still traveling at the same speed, but now the source is also moving and it's squashing those waves. On the left side, because the source is moving away from the direction that the sound is traveling, the waves are getting stretched out. Okay, so if you think about when we were talking earlier about long wavelength versus short wavelength, we could say that those waves that are getting stretched out are going to the red side of the spectrum, and the waves that are getting squashed are going toward the bluer side of the spectrum. Okay, so when we do this for light instead of sound, we can actually observe this effect if an object is moving away from us or towards us. On the top is just a simple spectrum of a star that's sitting stationary with us. But if the star is moving away from us, you see how all of those lines get shifted towards the red side of the spectrum. And then likewise, if it's moving towards us and the spectrum is blue shifted, we see the lines go to the blue side of the spectrum. And I want to point out that this amount that we're showing here is extremely exaggerated. An object would have to be moving maybe about 10% the speed of light to be able to see that much of a shift there. Okay, but it is real. Probably not quite 10%, but it'd have to be moving really fast. Okay. The other thing I want to point out is that this only works for motion directly away or towards you, something called radial motion. It will not tell you about this kind of motion. So we can at least tell if things like the Andromeda galaxy are moving towards or away from us. This one's moving towards us because the spectrum of its stars are slightly shifted to the blue side. Okay. Exoplanets, planets orbiting around other stars, we typically cannot see those even as a speck in an image because even the nearest star is so far away, the planets orbiting are usually lost in the glare of their parent star. But as you can see in this diagram, we have a small star, we have a massive planet. The star is still much more massive than the planet. But as they orbit, the star isn't just staying put. It's moving around too because they're both orbiting a gravitational balance point called the center of mass. If I made the planet even more massive, then the star would move in an even bigger orbit. Okay? So we can't see the planet, we can't measure any of the light coming off, reflected off of its surface, but what we can do is observe the star and observe its spectrum over time. And as you can see, as the star is moving away, and now it's moving towards us, the spectrum gets shifted to the blue, and then as it starts to move away, it gets shifted over to the red. So we can detect this shift. In fact, the first exoplanets were detected this way. Let's see, there was one other thing I was going to mention, and I forgot what it was. It'll come back to me later on. But anyway, so this is the Doppler effect that's used for actually discovering things like exoplanets. The Doppler effect is also the principle of how Doppler radar works. So you can detect wind motion on radar due to the motion of rain droplets reflecting radio waves. If the rain is moving towards you, then you see a slight decrease in the wavelength of the reflected radio waves. So you can actually learn a lot, with the Doppler effect. How are we doing on time? We're actually doing pretty good. Okay. Final thing I want to talk about before we just mention the images is how do we determine things like temperature? Here are three what are known as Planck spectra of different temperatures. And so a black body or a hot solid object, if you were to measure its intensity and the colors that it emits, then you would see that you would get this very distinct shape. It's called the Planck spectrum. So you can kind of see it looks like a bell curve that's been kind of lopsided there a little bit, but it's those black lines. Those black lines are showing the model spectrum for a star that's about 4,500 Kelvin at the bottom, about 6,000 Kelvin halfway up, and then the really tall one is for an even hotter star at 7,500 Kelvin. There's two things I want to point out here. First of all, and it's kind of hard to see, especially for those in back, but the peak of the curve, it shifts left or right depending on the temperature. That's something called Wien's law. And the lower the temperature, the more towards the red the peak is. So I don't know if we can see, let me see if I can get it on the screen here. Oh, there it is. Some of you may be able to see it on the screen. I didn't enlarge my pointer, I apologize. But our peak for our smaller curve is right over here in the red. The peak for the middle curve is in the green, like our sun. And then the peak for the really hot star is over in the violet. So the peak shifts left and right, and you'll also notice that the hotter an object is, the brighter it is. So if I had two identical stars, same radius, they'd have to be different masses, but let's imagine they're the same radius. If one was twice as hot as the other, it would actually be 16 times brighter than the cooler one. So temperature affects the color of the star, it affects the brightness of a star. And one thing I also want to point out, when we were talking about this red shift and blue shift, the colors of the stars that you see in the night sky, whether it's a red star or a white star or a blue star, is not due to this. A star would literally have to move about a quarter to half the speed of light for you to see a change in its color. The color is due solely to that temperature. Okay. All right. Let's see. So you may say, well, that should be easy enough. We should be able to take a spectrum of a star, figure out where the peak is, and voila, we have our temperature. Well, it's always easier said than done because here are three sample spectra. And you can see that it's very noisy. Each of these different spectra, which are different colors, have these dips in them. There's irregular shapes due to lots of absorption. In fact, each of those little dips is one of those black lines in the spectrum. So the point here is that, yeah, Wien's law on paper sounds really good, but in practice it's very difficult to do. Okay, and actually, speaking about temperature, I want to point out this lady, Annie Jump Cannon. She was an astronomer. She was actually what we would call a human computer. She worked for the Harvard College Observatory, and she was one of many women that were hired to go through, I mean, literally thousands of spectra, thousands of other observations, do computations, do cataloging, and all that good stuff. But in her work, she ended up revolutionizing how we classify stars, and it's a system that is still in use today. So her job was to classify stars by their apparent spectrum. Okay, and the original classification scheme started out as A, B, C, D, basically going through the alphabet. In the end, she realized, you know what, we're doing this completely backwards. All of these letters over here, they're completely obsolete. These are actually showing the same thing, and they're not in the right order. So when it was all said and done, she had simplified the classification scheme down to 7 letters that were then each subdivided 0 through 9. And it's a spectral scheme that we use today. But she would end up classifying several 100,000 stars in her career. In fact, she became so good that she could look at a spectrum and identify what kind of star it is within about 20 seconds. And we're not talking about a really nice, pretty spectrum. We're talking about stuff like this, okay? So to me, like those 3 bottom spectra look absolutely identical, but she would be able to pick out features to say, nope, this is a B5, this is a B8, this is a B9. So yeah, she was incredible at what she did. And yeah, it's a system that we still use today. But here is the classification scheme. So what she realized was that these differences we were seeing in the dark lines, these absorption lines, were actually dependent upon the temperature of the star. And when she started getting them organized to where they really kind of flowed well together, she realized that, hey, we've got it now in order of temperature. So if you look, especially on the right side, there is a faint red line right through here that as you go up, which means you're going up in temperature, that line gets darker and darker. So you can see how temperature plays a role in the appearance of some of these lines. These other lines in the violet, the blue, and the green, those are also due to hydrogen, and you can see how they vary with temperature. At the very top, we have our very hottest stars. And I know it's hard to see in the back, but those have very few lines visible. And the reason is that they are so hot, they produce so many high-energy photons that they typically ionize most of the atoms that would otherwise produce those dark lines. Okay? So if we find a star that has basically very few lines, we know it's a super hot star. Conversely, go down to the bottom to this line right down through here, to M5, and you can see it's just loaded with those absorption lines. Now the stars are cool enough where you can even get molecules forming, and they have their own spectra. So the temperature of the star does play a huge role in what the spectrum looks like. So you can still take a spectrum and identify temperature using the spectra, especially paying attention to the intensity of those dark lines. There's a different way, though, something called a color index, and this is usually easier and less time-consuming. But what we have here is a graph showing 7 different star spectra. At this time, hot is at the bottom, cool is at the top. Okay, and you can see how those spectra change shape as we go from hot to cool. But let's imagine I take a camera, it's a black and white camera, and in front of that camera, I put a red filter that's only going to let through red light. I put that on my telescope and I take a picture of a star. The star is going to appear a certain brightness through that red filter. But now I'm going to take that red filter off and replace it with the green one. And if you look, depending on the temperature of the star, the red image might be brighter or the green image might be brighter. So for example, at the very bottom, we have, in this red band here, you can see that the star, the very hot star, would appear somewhat bright in red, but it would appear much brighter in green and even brighter in blue. Okay, so we could take 3 different images. Now let's go up to a star like this F5 star. Fair amount in red, a little bit more in green, but almost the same amount in blue as we had in green. This really cool star has a lot of red, less green, and even less blue. So by taking images of these stars in these different filters and comparing the brightnesses, you get something called a color index. And that color index is directly related to temperature. In fact, this is one of the key ways astronomers will quickly get a temperature of a star. In fact, you can take an image that might have several thousand stars in it, and you're getting an image of all of those stars in a red, green, and blue filter all at once. You run those images through a computer, it'll calculate the difference for you in the blink of an eye, and then all of a sudden you now have the temperatures of hundreds to thousands of stars. Whereas doing it by spectra, you might have to take one spectrum at a time, which can take a while to do. Okay. All right. And then final thing, we'll end with some pretty pictures here and some application of this. So this is the Eagle Nebula. This is one of my favorite objects to try to image when I get time to image. This is what we would call a true color image. So if your eyes were as big as basketballs and could magnify really well and were super sensitive, this is how you would see that nebula in the sky. Notice it's got kind of a distinctive reddish pink color. In true color images, that tells you right away that that is hydrogen gas, because hydrogen is by far the most abundant gas in the universe. It'll make up about 98% of all of the atoms in a nebula like this. Okay, this is a region where stars are being formed. In fact, it's lit up by stars that have formed from its gas. So that's the telltale sign of hydrogen there. This would have been taken with what we call a monochrome camera, which is a camera that can only see black and white. And we would have taken a red image, a green image, and a blue image. Put them all together and you get your color image. Okay. This is not a new concept. If you look at a computer screen or take a little drop of water, a little drop, and put it on your phone screen, that will act as a lens and you'll see the pixels. So every color on your screen is due to individual pixels lighting up in red, green, and blue and varying intensities. So in the red part of my picture over there, only the red pixels are on. In the blue, only the blue are on. In the green, only the green are on. But that yellow area between the red and the green, that's where both the green and the red pixels are on. And so that color comes to our light and to our eyes, and we perceive it as yellow. So you create all these different colors of the rainbow just by using varying intensities of red, green, and blue. Okay, and so that's what we were basically doing here to get this nice color image. But it may come to surprise you that all cameras can only see in black and white. That's including your phone cameras. That's including if anybody has an SLR camera, or I should say digital cameras. The sensors, the little chips that are registering that image, they can only detect the amount of light coming into them. They cannot distinguish red from green, from blue, from yellow, or anything like that. So in order to be able to do that, especially with like the camera in your phone, the camera itself, like we have in this diagram at the top right, it has a set of filters that are pixel sized, and they're overlaid across those pixels. So like in the top left corner of this chip up here, that first pixel, it has a blue filter, so it's only going to detect blue light. Okay. The ones right around it are going to detect the green light, and then there's even some in there that have red filters that detect only red light. So once an image is taken, the onboard electronics go through and they say, okay, these certain pixels I know only look at green light, let's measure their intensity. And it does it for the red and for the blue, and when it combines all that information, it recreates that picture into a color image. Okay? So if it wasn't for that filter setup there, you would just have black and white pictures all the time. Okay? And I'll give you an example of this in just a moment. So we saw this as the true color image of the eagle, but there's also false color imaging. So this is basically the same region, but we didn't, the person who created this didn't just take that nice image we just saw, or take an image like that and run it through Photoshop to make the red look blue. This is done a slightly different way. So this image was also taken using 3 different images that were looking through different colors. But in this case, we didn't just do red, green, and blue filters. Okay. By the way, that center part, right in the very center of that nebula, you zoom in on it, that's the iconic eagle from the Eagle Nebula. Very famous part of the nebula image by Hubble, often called the pillars of creation. These are areas where stars are forming. That tiny little section there is a few light years tall. Okay, so humongous. Stars are still in the process of forming there. But anyway, that true color image, the filters used, they're called broadband filters. So what we've done is taken the entire rainbow, which runs from 400 to about 700 nanometers, and we put 3 filters up there. These are called the band passes. So you can see the blue area, that's the part of the rainbow that the blue filter would have let through to the camera. The green is where the part of the rainbow the green filter would have let through, and red is where the red filter would have let through. So you see we're getting basically the entire rainbow there. Okay. The image we just saw, that really kind of funky looking Eagle Nebula, it was taken using broadband filters. So now you see we're letting through just a very, very tiny part of the rainbow. In fact, these filters are designed so that they only let through the emission colors of oxygen, hydrogen, and sulfur. Okay? And you can get other filters that will let light from other atoms through. And then when you get your 3 different images, you say, okay, I want my oxygen filter to be the red, I want my sulfur to be the green, I want my hydrogen to be the blue. And you combine those together in the computer, and that's when you get an image like this. So when we're looking at something like this, the color is actually going to tell you what atoms are emitting right there. So in this case, I believe that the hydrogen was color-coded blue. So wherever you see blue in there, that's telling you where the hydrogen is. Wherever you see green, that maybe is where oxygen is. So these 3 filters, the hydrogen, sulfur, and oxygen, color coding those to certain colors is called the Hubble palette, because that's often what is done to a lot of the Hubble science images that we see. And just kind of give you a real world example of this, let's finish off by zooming in to the Cat's Eye Nebula. So this is something we saw previously. It's a target you can actually see with a small telescope in the constellation Draco. It's a small star that has died. Through a larger telescope, you can actually start to see some of the structure of the nebula. And it's actually conveniently placed next to a little star, so you can really tell the difference in a telescope. So here is the Cat's Eye Nebula. This is one view of it from Hubble. But let's look at some of the images Hubble actually used, or actually took, okay? Here's one. So this was the Cat's Eye. This is a processed image, but this is basically what came straight from the camera on Hubble. When it was looking through a filter that only let through the light of nitrogen. Okay, that's what the N stands for. And in this case, the 2 means that nitrogen has lost 1 electron. Okay, so whatever light you're seeing coming through there, ignoring the background stars, that is light just from nitrogen atoms. Let's do the same thing, but with sulfur. You can see it's somewhat similar, but it does have its differences. So there's nitrogen, there's sulfur. Now let's do one with oxygen. That one you see completely different. Okay. I think the one image we just saw, that nice colorful image, was actually like 6 different images, but they often will do multiple filters just to where you can see where all these different elements are located, because not only do you see where elements are dispersed, but their relative brightnesses can also tell you about like density and temperature. So let's take those 3 images we just saw. Let's make this image green. Let's make that image yellow and that image red. Okay, so red, yellow, green. And when we combine those, we get this image. And that's one that you would have seen. Okay. So again, just so Hubble, its cameras doesn't have that filter right over the chip. The filters are actually held out in front of the camera, and they can be changed out. Okay. So you're seeing some of the true black and white images there. So with that, yeah, we'll just end on that pretty picture, and I'd be happy to take any questions you might have. By the way, I can't remember if I told you, you do get to keep the glasses. Just don't look at the sun. Promise me you won't look at the sun. You get to keep them. Were there any questions? Yes, in the very... Oh, and we do have microphones. We're going to walk around so everybody can hear and folks at home can hear.
Is this thing on? Okay. How do they take photos of the light spectrum, or how is that captured back in the day, especially when Annie Cannon?
They would have literally had a prism built into the back of the telescope that would have gone between the optics of the telescope and the photographic plate. When you walk out to the front lobby, there's a little instrument that looks like two telescopes. That's actually a spectrometer that's more for, eye observation and doing work in the lab. But yeah, you would literally, back in the day before something called diffraction gratings were invented, you literally would have a prism on the back of the telescope. Sometimes it would be a couple of prisms. So you take one prism would start to break apart the light, then the second one would take part of that and break it apart even more. So the prisms aren't as good at producing a spectrum as the diffraction gratings, like what you have in your glasses. The gratings on the back of a telescope are even better than what you have in the glasses. They produce very crisp, clean spectra versus the prisms that would have been on previous telescopes. Yes, so you would get your telescope pointed at the object that you want. You'd have the whole spectrograph instrument installed on there, and then it would take the light, it would break it apart, and it would send it out, and that would focus to a photographic plate, and you would just take that spectrum there. And if your setup was good enough, then you could take one spectrum, you could cover up the plate right quick, and then move it to another object, open it back up, move the plate up just a bit, or move the plate up, then open it back up, and you could take another spectrum below that, so you could get multiple spectra on the same photographic plate. Yes?
I really come with a bunch of physical astronomical questions.
Okay.
But the only one that pertains to what you say, does our sun then rotate too, or move around according to your thing you said?
Yes.
With the planet and that one sun there? So our sun does that too?
Yes, let me pull that back up. So yes, in reference to this, yes, our sun, which, let me start by saying, our biggest planet is Jupiter. It is, if you took everything else in the solar system, excluding the sun, and compacted it together, you still wouldn't get an object as big as Jupiter. But Jupiter is 1,000 times less massive than the sun. You could do the calculations to figure out how much, but with Jupiter and Saturn, especially if they're on the same side of the sun, they together will move the sun about a sun diameter. So Earth, it basically does nothing. But yeah, Jupiter, if you just had Jupiter, the rotation point would be just about at the surface of the sun. Just like with the Earth-Moon system, we always think about the moon going around the Earth, but in fact, we're both going around a point that is about, it's about a quarter of the way to the center of our Earth. So Earth is wobbling around too, but because the moon is 80 times less massive, it does most of that. So, and then in addition, our sun even spins on its axis.
Itself.
It does, yes. And when we're observing the sun with a special telescope that only lets through the light of hydrogen, because of that rotation, if we're looking at one side of the sun, and then we go to look at the other side, we have to adjust the filter on our telescope because the side that we were first looking at, it maybe is moving away from us, and we've got it set up to observe that. But the other side is now moving towards us, so we have to adjust the filter a little bit because that side is slightly blue shifted. So we can even detect the rotation of the sun
Which axis does they rotate?
So if the sun's like this and the planets are all going around basically the equator, the sun is spinning like that.
Other way.
No, it's spinning the same. The sun is spinning the same way that the planets are orbiting around the sun.
And at what rate?
It takes the sun about 1 month to spin, but because it's a big ball of gas, the whole thing doesn't rotate at the same rate. The equator actually spins a little bit faster than the poles. So if you watch a sunspot, it'll take it about 25 days to go around the equator, but gas at the pole takes about 30. Okay. Oh, and we have some questions online too. You want to do one of those? Oh, yeah, I guess we could do a microphone, yeah.
So this is the first question online.
Hold on.
Okay. What would the Cat's Eye or Eagle Nebula look like in real life? What colors would you see with the naked eye?
So if you could actually see the Eagle Nebula with the naked eye, well, if we're talking about if your eyes were super sensitive, like giant telescopes, the Eagle Nebula would basically look like this to your eye. The cat's eye would actually look rather green because it's got very prominent emission from oxygen. In fact, this nebula here, this one is actually, well, it's kind of spread across the sky, but it's actually very hard to pick out unless you're in a super dark location and you've got a good-sized telescope. You can see the stars, but the gas is very hard to pick out. The little cat's eye is remarkably bright. It's much more concentrated, but your eye is actually most sensitive to the green part of the spectrum. So it works out great that the cat's eye and other what are called planetary nebulae tend to emit a lot from their oxygen atoms, which is green light. So they tend to be brighter to our eye. So in a telescope, your eye would still just pick out kind of a grayish color, but if they were super sensitive, you'd see more of a green color.
Could a tachyon exist, like a kind of particle that moves faster than light?
Good question. I don't even know if a tachyon is still theoretical. Are you a Star Trek fan?
No.
Oh, you're not? Okay, because that's why I hear tachyons all the time, and they're always wreaking havoc. So I honestly don't know if a tachyon is even proposed to exist, and if it is thought to maybe exist, would it travel faster? I don't think it could travel faster than light. It might be able to travel at the speed of light if it doesn't have mass, but I honestly don't know anything above what I've heard on Star Trek. So. We'll do one more online, and then we can alternate.
Go back and forth.
Okay, yeah.
Okay, the next question from online is, would an electron still have its energy even if it was in ionization?
Yes, so when an electron, let's say it's a hydrogen atom, and it receives that 13.6 electron volt or higher photon, yeah, it goes careening off and it's still got that energy. Now that electron might encounter another electron, it can even encounter a photon, and you get something called scattering, but it can transfer some of that energy. You can kind of think of like, billiard balls. You have one moving along really fast and it collides with a stationary one. Depending on how they collide, both of them might go kind of careening off, or the electron or that one billiard ball might end up stopping and transferring its energy to the other one. So it can interact with other particles, it can interact with photons, but it can transfer the amount of energy. And it could even gain more energy after an interaction. Who was next here? We'll do up here, and then Hannah, if you've got somebody there.
Do all stars produce light?
Do all stars produce light? Yes. So if they are an actual active star, not as in a dead star like a white dwarf, they are producing their own light.
why do, I'm not sure the definition of a planet. Why do some planets produce light and others don't?
So planets aren't really producing their own light. When we've got, a situation like, where did it go here? There. So we're mostly seeing the reflected light from that planet. Like if we're looking in visible light, we're going to be seeing reflected light from the star. The star's light can also be absorbed by the planet and re-emitted as like infrared light. Planets can emit some of their own energy just because gravity might be in the process still collapsing them down. So you take a gas and you squeeze it, it heats up. So if you've ever pumped up a car tire, after a while the hose that you're using to pump up that tire, it heats up because the air being compressed in it. So as a planet is collapsing down to become its final size, it can give off energy, but it's not going to be the same process that energy is created in stars. That's solely through fusion. Or I shouldn't say solely, but mostly through fusion.
Why do they call Mars then the red planet? Or when we see Saturn, we're not seeing the gas, the light of Saturn.
Right, so we call Mars the red planet just because in our sky we're seeing it as red because sunlight is reflecting off of it, and because of the iron oxide in its soil, it tends to reflect more of the red light. Okay.
Are electron volts the same thing as regular volts? And
No,
how are those measured?
electron volts are, it's very confusing. Electron volts are a much lower energy. I don't know how that actually compares to an actual volt, but yeah, it's much less. Let's do a couple more questions, and we're going to get your question over there too, and then we'll break. And if you have other questions, feel free to come up. Yeah, let's do a couple more here.
Okay. If hydrogen came first, was red the first color?
Oh, y'all are making me think hard tonight. If hydrogen came first, would that have been the first color? So early on in the universe, if we have just after the Big Bang, hydrogen would have formed. We would have had some helium form in that as well, but we're at a point in the universe's history where it is still so hot that the atoms were still completely ionized. So we wouldn't have had any of these individual colors being emitted. So I guess once the universe did cool down, red would have been one of the colors to come out, but we would have had emission from helium as well. So probably just a little bit of the rainbow, but not every single color of the rainbow. I don't know if that's a satisfactory answer or not. That's a hard one. Let's do one more over here.
How fast does light travel at miles per hour?
Oh, good question. How fast does light travel at miles per hour? It's about 186,000 miles per second. So we do that with, multiply that by 3,600. I want to say I used to know this, but whoever has their calculator handy, it'll probably be a familiar number, but I can't remember how many miles per hour that would be. Actually, I think I do. So this light will travel 93 million miles, the Earth's sun distance, in 8 minutes. So multiply that by about 7.5. So 93 times 7.5. That'd be about 750 million miles per hour. Somebody check my math on that.
669, thereabouts.
669 million?
Yeah.
Okay, so not too far off. All right. Okay, we'll do one more question, and then, we'll break.
Why is it green and not yellow and like the primary colors of light?
Why is the green and not the yellow the primary colors of light? That I would have to think a while about, and I don't know if I'd have an answer for that.
Well, yellow is a mix.
Well, when we have, so I mean, we can, I guess that's the key. You can create any of the other colors from red, green, and blue and their combinations. So you can get yellow from the red and the green if you're using light. If you're using paint, you get brown. Yeah, and then the blue and the green gives you indigo, and then violet is red and blue. So yeah, that's a good point there. So that's not to say, like, if we see an element giving off yellow light, that it's a mix of red and green, like sodium. Those old style orange lights that you'd see on the streets of sodium lights, that's actually sodium in there, and that yellow is actually two very closely related colors of light being given off, and they were truly a yellow color. All right, we got one more.
We have one more
Okay, we
online.
have one more up there, and I know I keep saying that, and then we're going to break.
Okay, yeah,
what's
this
our
is the
final
last online. Okay, when there is gravitational lensing by massive objects, is there an accompanying Doppler shift?
There's gravitational lensing, so that one I wouldn't think so, but I honestly don't know. So when we're talking about gravitational lensing, we're talking about like I'm trying to think if I have that presentation. I don't think I do. But anyway, if a massive object, let's say we have a big black hole way out in the universe, as it passes in front of a background star, the gravity of the star actually bends space and time and causes the light from the star that's way beyond the black hole to be focused around to us. And so all of a sudden we see this bright point. I don't think it would create any sort of a Doppler shift. That's going to be my final answer, but they're definitely going to have to consult Google on that. And so, if you all have any other questions, please feel free to come up. I'm going to be here, until the bitter end. But thank you all again for coming. Is it clear out? Do we know? Everybody's saying yes, so we're going to go with yes. I think that we are looking at a star system called the Double-Double. So when you go up to the telescope and you look in the eyepiece, it looks like two bright stars, but then carefully look at those two stars and you'll see each one is actually a pair. There's one pair like this, one pair like this, and they're actually all orbiting around. So it's a pretty little system there. But again, thank you all for coming, and thanks for the folks at home for tuning in. And if you have any questions about anything, please don't hesitate to come ask me. And have a great night.